You're enjoying sitting outside when suddenly the sun peaks above the tree that previously blocked it and hits you in the face. You conclude that the sun must have moved up in the time that you were sitting outside. So then you start thinking, is there a way to know exactly how high the sun is? Like calculate it using your time and your location? I asked this exact question myself, so I decided to try to solve it. And after many equations and many graphs, I've come to an answer, so I'm sharing it with you today. The first question I had was, how do you even measure that? You can't just be like, oh yeah, the sun is 1,000 meters high and before it was 950. So instead of distance, we use the angle above the horizon of the sun. You could also think of it as the angle in which the rays of light from the sun hit the ground. We'll call this angle the sun's elevation. Let's zoom out so that we can see the entire Earth. We're going to be using a lot of diagrams and graphs to help us solve this problem because we're going to have to find a lot of relationships between different angles, different side lengths, etc. They also help us conceptualize the problem. The line that connects the center of the Earth to your location represents directly up, and the plane representing the ground is perpendicular to this upline and tangent to this circle. Still, the sun's elevation is the angle between the sunlight and this plane. The sun's elevation is all dependent on how tilted this plane is, either up or sideways. This vertical and horizontal tilting can be measured using a vertical angle and a horizontal angle. So how exactly does the sun's elevation depend on this vertical angle and this horizontal angle? And how do we find these two angles? These are the two big questions to answer. Tilting the plane relative to the stationary line of sunlight is the same as tilting the line of sunlight relative to a stationary plane. Since we care about how the line is tilted, we need to find a way to describe how the line is tilted in terms of how the plane is tilted. Tilting the plane vertically v degrees is the same as moving the line down v degrees. And then tilting the plane horizontally h degrees is the same as moving the line h degrees in the perpendicular direction. So if we make this circle's radius 1, then we can create this right triangle where x is the distance between the sun and the ground. And we know that getting the inverse sine of x would find us the sun's elevation, s. So how can we do that? Well, let's just see x. If we look at the situation from the side, we see x like this. This angle here is going to be 90 minus b. So if we figure out this side, then we can find x. Well, this side is just going to be this here, which is going to be sine of h. Okay, so now we have that. So we know that x is just going to be equal to the sine of h, because that's the hypotenuse, times the sine of 90 minus 3. And because of the sine cosine rules, sine of 90 minus x is equal to cosine of x, we can replace the second part with cosine of v. Okay, so now we know x is equal to sine h cosine v, so the sun's elevation in terms of h and v is going to be the inverse sine of sine h cosine v. Now that we know this, let's figure out how to find v and h. Our vertical position can be expressed using latitude, the angle between the equator and your location. But it doesn't make sense for the vertical angle to only be determined by the latitude, because your latitude doesn't change, but you might have noticed throughout the year, the highest the sun gets does change. So there must be another factor. Although the Earth is always tilted the same direction relative to the background stars, since it orbits the sun, it's tilted in different directions relative to the sun. This tilt ranges from plus 23.4 degrees to negative 23.4 degrees. This we call the solar declination, and it moves your location up and down relative to the sunlight line throughout the year. It doesn't change linearly, but we can approximate it using a sine equation, or we can use something called the Analemma. You find the date that you want, and then you see which declination it corresponds to on the left side. Now, how can we describe the horizontal position? We know that Earth rotates daily, so our location is constantly traveling on a circular path around the Earth's axis. When solar declination is 0, this path is flat, but when there is solar declination, this path gets tilted, so it also adds to vertical position. So how can we understand their position on this circle? The Earth is always divided between the side that sunlight reaches and the side that sunlight doesn't reach. The line in between is called the Terminator. The sun rises and sets when your location passes through the Terminator, and it reaches the highest that it will get during the day halfway in between at noon. So it seems like we can quantify our position using time. Time is based on the position of the sun in the sky, but because of our timing conventions, clock time is not always perfectly accurate to the sun. So right now I'm talking about real solar time. If the sun's peak is at noon, then the opposite is midnight, and in between would be 6 a.m. and 6 p.m. We can find our angle on this circle by dividing minutes by the number of minutes it takes Earth to rotate 1 degree, which is 4 minutes. So our angle from 6 a.m. would be minutes since 6 a.m. divided by 4. I'm going to call this the time angle. So this allows us to understand our horizontal position. But if you want to find the time angle that's accurate to the sun using clock time, you're going to have to understand our timing conventions and how to uncover true solar time. Have you ever seen those photos of a bunch of suns making a figure 8 in the sky? Well, this is all about that. But if you'd rather just see how to find the sun's elevation after you already know the time angle, then you can skip ahead. Although I do have some really cool graphs towards the end of this section. First of all, the time on your clock is not specific to your longitude, but rather a time zone, which is a collection of 15 longitudes. To correct this, you can find the time at the Universal Coordinated Time Zone, which is centered around longitude 0, and then you can add your longitude times 4, which is the minutes you are ahead or behind the Universal Coordinated Time Zone. Okay, now for some really interesting stuff. Because of a combination of Earth's elliptical orbit and its obliquity, or tilt, the sun does not appear to orbit Earth at a constant rate. And so we get the equation of time. So a sidereal day is when Earth makes a 360-degree rotation. And is this not a day, you ask? Well, it's actually not, because by the time it finishes its 360-degree rotation, it's orbited a little bit, so it has to rotate a little bit more in order to face the sun again. According to Kepler's second law, a line connecting the sun to a planet sweeps out equal areas in equal intervals of time. Because Earth's orbit is elliptical, this means on one side the Earth orbits slower than on the other. And because the orbit speed is changing, that means the additional amount of rotation the Earth has to do each day changes, resulting in shorter and longer days, or the sun appearing to move slower or faster. This is a graph of the average sun in blue, and then the real sun in purple, and you see it gets behind and ahead of the average sun throughout the year. So that's the first factor that influences the sun's pace. To understand the second, we'll look at space from the perspective of Earth. We see Earth's axis tilted against the orbital plane, where from our perspective, the sun is traveling across. And then the equator can be projected out into space. We call it the celestial equator, and we see it's tilted against the orbital path. Now, what if we oriented ourselves so that the Earth axis pointed upwards? Now the celestial equator is flat, and the sun's path from Earth's perspective is on a tilt. So remember, the length of the day is determined by how long it takes for a location to rotate back around to face the sun. So because Earth is rotating around its axis, we don't care about when this cross-section reaches the sun, we care about when this cross-section does. In other words, our timekeeping is not based on where the sun is on the tilted path, but rather where the sun is projected onto the celestial equator. You can see the projected sun is slowing down and speeding up because of the tilt of the real sun's path. If we exaggerate the Earth's tilt a bit and view this from above, you can see the projected sun swooping across the sides and slowing down at the top and bottom. Let me speed it up some more. That was fun. The sun slows down while crossing the celestial equator because it takes longer to travel diagonal than straight. The projected sun speeds up at the top and bottom of the tilt because in these places, it's traveling close to parallel to the real sun. I also made this animation which lets you see the average pace of the sun, and you can see how the projected sun gets ahead of it and then behind it, and on the equinoxes and solstices, they align together. Remember, it's a little bit counterintuitive, but a faster sun in orbit means a slower sun across the sky because it takes longer for Earth to rotate back to face the sun. So here we have the graph showing the effect of the Earth's tilt on the equation of time, and the places where the sun is behind correspond to where the projected sun is ahead of the average sun. You can match these dates in the graph to the milestones in the previous animation. So if you add the effect of elliptical orbit with the effect of the Earth's tilt, you get the equation of time. So in this valley, the sun is 14 minutes behind the clock. At the big peak, the sun is 16 minutes ahead of the clock. So how can you get the value of the equation of time for the date? Well, there's an equation that approximates it, but also we can go back to the Analemma. The x-axis is the equation of time. On the left, the sun is ahead of average or fast, and on the right, it's behind average or slow. You can see that there are 4 neutral points where equation of time is equal to 0, like there's 4 x-intercepts in the graph. And also we have the mini valley here, the big valley here, the mini peak here, and the big peak here. So the graph explains why we get the figure 8 really well. The way that people capture this figure 8 in the sky is they take a picture of the sun at the same time of day on different days throughout the year. So finally, solar time is equal to our longitude time plus the equation of time. Let's just run through the whole example. So that gets us to 2:52 p.m. for our longitude time. Now, in order to find the equation of time, we go to the Analemma and we find the date August 1st, and that corresponds to a value of about 6.5 minutes behind. So we have to subtract 6.5 minutes and we end up with 2:45 or 0.5, which I'll just round up to 2:46 p.m. And finally, we know that the real solar time is 2:46 p.m., so we can use that to find an accurate time angle. So 2:46 p.m. is 526 minutes from 6 a.m., and 526 divided by 4 is equal to 131.5. So now we know how to express our location in terms of the time angle, the latitude, and the solar declination. So remember, we know that S is the inverse sine of sine H times cosine V. So originally I solved for H and V separately and then plugged them back in. But then eventually I realized there's kind of a shortcut. Instead of finding H and V separately and then plugging them in, we can instead find a segment that has the length of sine H times cosine V and figure out how to find that segment's length in terms of L, D, and T. If the sphere has a radius of 1, then this segment is equal to sine H times cosine V. Remember, these are the horizontal and vertical angles. This segment is equal to cosine V. Knowing that, we can make a right triangle here, and this angle is the horizontal angle, and so this leg is equal to cosine V times sine of H. And that's exactly what we're looking for. Now, how can we express this segment in terms of L, D, and T? Well, we can break it into these 2 parts. This first part depends on the declination and the latitude. So this is sine L, and this is D, so this is also D, which makes this segment equal to the hypotenuse sine L times sine of D. What about this segment? First, let's find this. We can use a right triangle here. T is the time angle. R is going to be cosine of L. So that makes the segment we're looking for cosine of L times sine T. Now that we have that, how can we get this? Well, we have the angle over here is equal to D because that's the declination. We can also show it. These are vertical. This is alternate interior. both of these pairs add up to 90, and they both have A. Now we know that this segment is equal to the hypotenuse cosine L times sine T times cosine of D. Okay, so altogether, this segment is equal to sine L times sine D plus cosine L times sine T times cosine D. So if we know that S is equal to the inverse sine of sine H times cosine V, and we also know that sine H cosine V is equal to this, we can just replace sine H cosine V with what we found, and we get our equation for S in terms of things that we know, L, D, and T. So that means just based on our date, our location, and the time of day, we're able to figure out the elevation of the sun. Miraculously, this is the same equation as online, even though they derived it in a completely different way. First, there is one subtle difference. Their equation uses cosine t instead of sine t, but this isn't a problem because their time angle is from 12 a.m. instead of 6 a.m. So RT is equal to their t minus 90, which means cosine of their t is equal to sine of RT. So the internet derived the sun's elevation using something called the spherical law of cosines. So we're dealing with 3 points on the sphere: the sun, the zenith, which is directly above head, and then the pole. And then we're connecting them with a spherical triangle. We label the sides A, B, C, and then one angle C. And the law of cosines tells us the relationships between these sides and this angle. Now let's try to figure out what each of these arc lengths are. C is the arc length between the sun and the zenith, which is the complement of S. A is the length between the pole and the zenith, which is the complement of the latitude. B is the arc length between the pole and the sun, which is the complement of the solar declination. And finally, we need to figure out what C is. Because the line of the pole is perpendicular to the path of the sun, the angle between the edges coming out of the pole match the angle of the sun's path. This is the time angle, and C is going to be the time angle minus 90 degrees. Okay, so now let's plug in all of our values into the spherical law of cosines. We could use some cosine/sine rules to simplify this, and we get the exact same equation that we derived in a completely different way. Something else exciting is if I do use the method where I solve for V and H separately and then plug them in, we actually get the exact same number as this equation. So this was the first way that I solved the problem. So when I saw that I got literally the exact same number as the equation online, I was so excited. I could not believe it. Because the process, it wasn't as straightforward as it probably looks in this video. It took a lot of thinking to get to these equations and trying to wrap my head around how the Earth is moving. Visualizing the problem with graphs was really helpful, and I also used the graphs to check my work along the way because they could calculate the angles for you. My graphs used to be a lot more busy. Also, I think a step that really helped was recognizing that I could view the movement of the plane as the movement of the line instead. I'm not sure what kind of problem-solving strategy this is. Maybe working backwards? I find these notes really funny. And as usual, it's really important to believe that you can solve the problem. Okay, thank you for watching, and I'll see you in the next video.